Hello everyone, welcome back to my salome next tutorial. So in this tutorial we are going to analyze remote load of cantilever beam. So we have taken a material of Young's modulus 210 gigapascal and Poisson ratio is 0.3. In this case we are going to do linear static analysis. So this is the case. So the cantilever beam of length 1.4 meter, that means 1400 mm, and diameter of the circular cantilever beam is 200 mm, that means 0.2 meter, and we are going to apply a eccentric load of 0.5 meter from the center. The force value we are going to apply is 800 Newton. So finally we will check this result with the analytical results. This is the actually analytical value. We will compare the result with FEA values. Now just go to open the salome. Salome is the free and open source finite element solver. Here we can create and geometry and mesh similar to ANSYS, and we can solve by using code aster. Now just going for geometry, go to new entity, basic, there is option called primitives, go to cylinders. Now I just want to create a cylinder in x-axis, base point is this, vector is x, the radius. Now just go to the geometry here. Here the diameter is 0.2, that means radius is 0.1. Just go here, radius is 0.1 meter, and length, height is, just go to the model here, the height is, length is 1.4 meter. 1.4. Go to fit screen. So this is the model. Now we are going to apply a load away from this center point. Just go to apply and close. Now I have created the model. Just go to create group, volume group. I'm just giving beam. Just apply face. The left side surface I am going to fix completely. So select this face, apply. This one is fix. If you want to see only the selected, so only the selected. So here you can see this is the face we have selected. Just apply it. So here we are not going to apply any load. One more point we are going to create here. With that we are going to give rigid connection. For that we need to create a surface here. So only this is actually I'm going to give as a master. Apply and close. So left side I'm going to fix, right side is rigid connection I'm going to use. This one is the beam. So now I will save this file. Go to Vengat, pictures, code aster, remote load. This is I'm saving as study 2. Saved it. Now go to mesh, create mesh. So as you see, select the cylinder, go to mesh, create mesh. Here I am going to create tet mesh of local length, whatever the local length it's showing 0.14. I'm just going to give divided by 10, it will make fine mesh. So 0.01, save OK, apply and close. Right click, compute. See, it has created very fine mesh. I just want to reduce the value. Right click is edit mesh. So I'm just change this value into 4. Say OK. Apply and close. Right click. There is option called clear and compute. Now it's look like very coarse mesh. I just want to change this value into edit mesh. Change this one into 2. Say OK. Apply and close. Right click. Compute. This mesh size is enough. So now we'll keep this mesh. Now we'll go for analysis. Now we'll check the groups. This is the groups we wanted. We'll save it. Actually we want to create groups to apply the remote load. So we need to create one node here. We need to create one more groups here. So for that just go here. So just there is a modification, add node. Now we need to specify the dimension. Just go to the model here. The length is x direction 1.4 and from the center is 0.5. So just go salome meca, x direction is 1.4. Here you can see there is one more red point. And we'll create in y direction. Y direction will make it 0.5. I'm just closing. Now just going here, modification, add node. So x is 1.4. Here I'm just 0.5. See here, this is the node it is created here. So just apply and close. Now I have created a node here. Then we'll create a group. Just go to mesh. There is option called create group. So here there is option, use enable manual selection. Select this particular node, add. Here these are things to be a node. This is the node number, it came here. Now we'll name it as load. Then we just give it as apply. Now see, there is a node group which is created here. Now just close it. Now right click this mesh one, go to mesh. There is an option called compute. Now we have created this load, a node group also. There is one more group we need to create as a node group to apply the rigid connection. That is, just go to mesh, create group. Now we just make it only so the master as well as this node group. So these all the nodes has to be connected with this node with the rigid connection. So to transfer the force, so just make it manual, enable manual selection. Just select these nodes by using box, make it add. Just close it again. Now just go to mesh, create group, enable manual selection, select these nodes, make it add. Now it is add here. Mesh one. Now we just name it as this one as a rigid connection, rigid CON. So I'm going to give solid connection to this, apply and close. Now again select this mesh one, mesh, compute. Now we have defined everything. Now we can save this file. Now we'll go for code aster or aster study to create the setup. Go to mesh, aster study. Stable, say OK. Now just right click, add a stage manually. Go to mesh. First we need to read the mesh. Go to read mesh. This is the mesh one. Format is MED. Just OK. Now we have read mesh. Then we need to create a group of, there is an option called create mileage. We need to use this one to create elemental group from the node group. So the name is mesh 0. Just remember this, we are creating a mesh 0 from the mesh. Just scroll down here, activate this mesh 0 first. Then just go up. There is an option called create POI1. That means we need to create a discrete element from the node group to element group. Choose the group of node, that is load. Say OK. We need to name it as a elemental name. Here the element name will not show because we don't have. We need to give us load, same name. Say OK. We are making this node group into an element group to apply the material properties and model. To assign the model and material property, we require elemental group. So for that we are renaming this load into load as the same name as a elemental group. Say OK. Just apply it. Now you see the mesh 0 having a elemental group of load. So this is we are doing it because we need to apply material and model to this load group. Just say OK. So afterwards we need to use mesh 0 only. Go to model definition. There is an option called assign a finite element. Finite element. Choose edit the group 3D element. Choose a 3D element. This is we need to assign as mechanical 3D. Now say OK. There is a one more finite element model is there, that is called discrete element. Just click this one, edit. So there is a element group, edit. Here the element group will not show. We need to manually name it as load. Say OK. Choose mechanic. This is actually a discrete. We have to choose discrete from this options. There is option called distr. So there is an option called distr. Yes, distr. Choose this one. Now just say OK. Now just there is an option called mesh. Just make it mesh 0. This is one thing we need to use. Mesh 0. Just apply it. Say OK. Now you see here, this volume element we have applied mechanic 3D. For that load, that particular single node, we have applied discrete mechanic. So now we have defined the model. We have one single node. We need to assign element property, that is afikara element. Just go here, element property. This is actually discrete element. So we need to choose discrete. So choose this one, edit. So there is an option called kara. Choose this kara. Here we need to choose KTRDN. So stiffness, translation and rotation. This is diagonal on the node. This is the meaning for KTRDN. We need to choose this one. After choosing here, you can see these are enabled. Just go to elemental group, edit. Here we cannot see the element group as load. We need to manually enter it, load. Here there is 6 options. We need to specify the stiffness value. I am going to specify as 0.1 to all. 0.1, 0.1, 0.1, 0.1 and 0.1. So this is the stiffness value I have specified. Node group I have chosen as a load. Say OK. Then here there is option called mesh model. Just choose this model, scroll down here, then you just apply it, say OK. Now we have specified the elemental property. Now just go to material, define a material. Now just go to the PPT. Our material is just simple steel. We can use the same material. Just go to salome, linear isotropic, edit. So Young's modulus is 210 e power 9 and Poisson ratio is 0.3. Just say OK. Just apply it. Say OK. Now we have defined the material. We need to assign the material. Go to assign material. Go to mesh. Here we need to choose mesh 0 because mesh 0 is the latest one. Model. We have model. Go to here. Everywhere. We can use assign everywhere. Choose it here. Material. Say OK. So everywhere it will assign the same material. If you want to assign different material, this is particular point, we can assign separately. Now all are same material. Just say OK. Now we have assigned the material. Functions. Here we are not going to use any functions. Leave this one. Boundary conditions. Go to assign mechanical load. Now we need to fix the left side. So just go to the problem. Left side we need to fix completely. From this surface to this node, we need to give a rigid connection. Here we need to apply force of in negative direction of 800 Newton. Sorry, 8000 Newton. that means 8 kilonewton. So now enforce degree of freedom, edit. First go to group of elements, edit. So there is a fix, choose it, say OK. We need to fix it XYZ. This is enough because that is our solid element. So only 3 direction fixing is, 3 displacement is we can fix. Go here. Now we have fixed left side. Now we need to give rigid connection between this here. So go to, there is an option called liaison solid. This is the rigid connection, that we will call it a solid connection. Liaison solid, just add it here, just go to edit. We have a node group, just choose the node group, edit, that is rigid connection. This all the nodes and this point node, make it OK. Need not to specify anything, just simply say OK. Now we have applied the rigid connection. Finally we need to apply one load here, so to the load group, that is there is option called force on the node. Just go to force on the node, edit, group of nodes, edit. There is option called node group. Choose this node group, load. In which direction means Z direction. Choose the Z. In negative direction we need to say minus 8 kilonewton, that means 8000. Say OK. Now just scroll down here, model, just apply it. Now you can see we have fixed the left side, we have given rigid connection, we have applied the load, everything we have specified. Save OK, apply, save OK. Now we have defined all. Now we just go for analysis, static mechanical analysis, material, structural element, go to loads, edit. Here we have one load, save OK, apply, save OK. Now we have defined the solver also. Now we'll go for force processing to calculate the one meca stress. So I want to see directional stress as well as the one meca stress. Directional stress we can choose from constraint. So sigma element directional stresses, then sigma nodal directional stress. Similarly we can choose one meca stresses, equivalent SIEQL node and SIEQ node. We can choose it, scroll down here, material, model, materials, elemental property, everything. Scroll down here, just apply it. Here we have unnamed, we have not changed the name, same name we can give, wrestling. Just apply, save OK. Now we have done post processing. Now we will save the results to view the results in paraview. Set output format, click this 3 point, go here, pictures, code aster. There is an option called remote node. Here remote load underscore 1.rmd. This is the file name I am giving. Save. Just here there is a result, just click it here, edit, choose the mesh has to be mesh 0. Here result is wrestling, choose calc champ. Element property, you choose this current element. Here you choose tau champ as yes. Okay. Now save OK. Make it the format med, just apply it. Now we have saved the results also, just save OK. Now we just save this file. Now we have defined everything. We have read the mesh. So to apply the material property and model, we have created the point node as a load. Then we have defined the model and element property. Then we have defined created the material. We have assigned the material. We have created the loads. We have defined the solver. This is for calculating the stress, one meca stresses, principal stresses, everything. Now we have done. Now we will go for history view. Click the stage 1. Click this one. Make it 5 seconds. Just run it. Now it will start solving. Just wait for a while, it will solve. If any error comes, we have to rectify it. This is a message file we are viewing here. Now it is solved. Here you can see. So every command it's reading. Now it is solved and it is saved the results with alarm. So now it is done. Now we'll go for paraviews to view the results. Go here, paraviews. Select this build one, open it. Pictures, code aster. There is a remote load. I have given a name for result file is remote load _1 RMDs. Just OK. Now choose displacement and apply it. There are different components it came because we have different element types. So this is the model. Now we just want to see displacement. This one is the displacement. If you want to see the stress, 1 meter stress, choose Reslin SIEQ node. Then apply it. Choose here SIEQ node. Choose 1 meters. To view the change the color, here there is an option called blue to red rainbow. Shortcut is came here. Then apply it. If you want to change other also, you can choose it here. Then close it. Make it this value into 12. So now you can see this, it's bending as well as torsional, rotating. So both the load are acting because we are applying the load eccentrically. The results is this one. Now we'll check the stress. So what is the stress value we are getting here is 14 megapascal. That means 14.9 into 10 power 6 Newton per meter square. Now we'll check the value here. We are getting 13 into 10 power 6. So we are getting almost a very close value. So to check the value here, as I already explained, so we'll check the value away from this point. So to see the complete value, so just make sure your view, Windows, selection display inspector is enabled. Now just choose this one to SIEQ. Now just select the surface nodes. This one is a select point on T, surface nodes. So now I've selected multiple nodes. Any one of the node value, we'll check it here. So now we are coming very close to 12, 13. So maximum values we are coming here. By increasing elemental size and by refining the mesh, we will get the accurate result, as well as by increasing the order of the element. If you have used a linear element, if you are go for a quadratic element, we can get very closer result to this. So this is the 1 meter stress. Similarly, we can see the how much it is got rotated, the angle of twist. In this point. So now we just go here. There is a point displacement. Just apply it. Now just go here. Choose the displacement. Rotation about, because so how much it's got twisted in about x-axis. So rotation about x we can choose. So this much is got rotating 0.0001. So we can check in that value. So in this tutorial we learned how to apply a remote load to this cantilever beam, and we have checked with our results in the analytical results, and we have compared the result with 1 meter stress. So thank you for watching my videos. If you want to see the displacement, Here we can that generate vector, apply it. Just go here, just apply it. This is more deformed. Now we can simulate this. Just go to animation, create new animation, just say OK. Now just simulate. Remove it. Now just change this value into displacement, apply it, go here, choose the wrap vector. Here we need to choose this one, delete. Displacement vector, go for this one, that make it here, then apply it. So now you can animate this. Go here, create a new animation track, say OK. Now just animate it. Now it is bending as well as rotating. So both the load will act here. So we have compared the results. So thank you for watching my videos. Please subscribe my channel for more videos. Thank you.